Okay, so in this talk, it will be start with my internship work. So those parts you may already know. Will be a very easy start. So we're about trying to use knowledge graphs and some neural networks to improve the representation, retrieval, and also understanding of our language. So most of this talk, the applications are in search engines. So we know search engines, and we use it every day. We have Google, we have Bing. But outside of Google and Bing, we also have the open source search engines. We have Elasticsearch, Solr. Here we have Semantics, Scholar. We also have academic search, and now email search is also a very hot topic. So we don't know what exactly happened in Google or Bing, but most times they have a very massive scale of user feedback information. So use that, they can do the web search, especially the head traffic very well. But here we'll start with is to have a very quick recap of how search engines is typically done in the public domains. And then we will build upon it. So typically, as ad hoc retrieval, we consider it as a retrieval or ranking task that you have the query, you have the document. They are both in natural language, and you want to match the relevant document with the query. So typically, this is done in 2 steps. The first step is text representation. You want to convert the raw human language into some format so that the computer system can easily process. And in search engines, this is typically bag of words. So you break down the language into individual terms, and then you count their frequency, and you map them into that discrete space where each dimension is 1 word, and maybe the weight is a frequency or inverse document frequency. And then after that, you need to match the query and document, which we call the retrieval or ranking in that space. So this was usually done previously by retrieval models. So there are almost mainly 3 signals to use: the term frequency, the frequency of query words appear in the document, the inverse document frequency, which query word is less common. If it's more rare, then maybe have more weight. And we also have the document length to normalize all these signals. And later in the new century, we have learning trunk research that we bring in the machine learning techniques into that system. So we combine all the previous retrieval models as ranking features. And also we have additional features, for example, click frequency and spam score and document quality, etc. So this is actually what you usually get from the open source search engines. In fact, I think Solr only have a learning trunk beta version last year or the year before last year. And Elasticsearch is just moving from a raw TF-IDF to BM25, I think the next version. And learning trunk is typically the state-of-the-art you will find in many track computations. So within this framework, of course, there are many limitations. The most intrinsic one maybe is what they call the vocabulary mismatch, that all the representation and the ranking of documents and query are based on words or phrase or n-grams. So if the terms in the query do not appear in the documents at all, there is still not much you can do about it. Also, it is a very shallow understanding. It's based on breaking the text into a bag of things and then counting that frequency and using all the manual features to combine everything. So there aren't many ranking signals as you would expect that can work well in the open domain. For example, in the learning trunk research, there might have been about 50 different models and all the different ways to train them. But many of them all use the same set of features, especially on the public world. So it leads to a very interesting scenario. It's kind of like a search dilemma that to be able to find something, you should have some knowledge about it first. For example, I can easily find something in Semantics Scholar about my research topic. But if it is in the system part, if in the security part, or even if it's in the medical domain, it will be very difficult for me to formulate a reasonable queries to find the things I want. Most of the time, I have to start with a Wikipedia page, read the article, figure out what are the right terms to use, and then issue it to a search engines to find the things I want. So this leads to the general motivation of my research that I want to improve search or revolute it from a retrieval tool, but more to an intelligent system. And make it something that, for example, at least do not need that large scale of user click information, but can still work well. For example, make Semantics Scholar improve its text understandings and make it work well even without the web scale user feedback like in Google High Traffic. But furthermore, I also wish the search engines can be able to understand more of our information need, can be able even to help us to formulate the queries and then to retrieve documents, but maybe not only the raw documents to us, but also some summaries of them, more more better process of the signals and to provide for us. And I believe the path through it, at least the one I'm taking, is through language and knowledge and understanding. So my overall research, you can consider it as 3 parts. So I started with trying to bring in the structured semantics from the knowledge graph to information systems. So this starts somehow with the internship work here. So I try to use the knowledge graph information to improve semantic scholar, but also web search and maybe medical search. And later I have generalized this idea towards more about general text understanding. So we wish to better understand text at a larger level, like documents, corpus, or the whole search traffic, using entities and events. And also I'm the main contributor of trying to bring in the neural networks into information retrieval. That we have experimented and developed a lot of models trying to learn the distributed semantics from the large-scale data and trying to use it to improve the understanding and retrieval of documents in our search engines. And also have many works in trying to better model the interactions between user and search engines, for example. So in this talk, I will start with presenting you the general framework of what we call entity-oriented search. And then I will give a more technical depth view of how we can use that to better improve the understanding of text in a larger scale. And later I will see how these 2 parts connect and also connect with the deep learning part and see how entities, words, phrases all work together in the neural network setting. So let's start with entity-oriented search. So the general intuition of this is very, very clear that we have the knowledge graph information, but here we have a word-based search engines. Can we use that information in the knowledge graph, all the structures, entities, semantics, to improve the understanding of query and documents and improve the search accuracy? So I'll give a very quick, broad definition of knowledge graph. So knowledge graph is actually a very new term. I think it's only 3 or 4 years old. People want to emphasize the graph part of the knowledge structure. People also have called it knowledge basis. I also consider the classical controller vocabulary as one form of knowledge graph. So to me, those are all structured semantics. So the general idea of knowledge graph to me is that they have all the human knowledge and we want to store it in some structured format so that our computer systems can use and understand. And examples of it include Free-based DBpedia, Wikipedia, and maybe also Microsoft Academic Graph and the Magic Controller vocabulary. So the information in the knowledge graph are usually considered as twofold. So those are mostly always stored around entities, so the nodes in the knowledge graph. For example, CMU is an entity, and Andrew is also an entity. And here, entity cannot just be named entity, but it can maybe also be general entities, for example, a MacBook, a table. So those actually also have free-based entries and also Wikipedia pages. So I consider all of them as general entities. And what makes knowledge graph interesting is all the structured information associated with all these entities. So we have, I want to move the screen over here so it's easy for me to see it. So we have all the nodes, then we have the relations that connects those nodes. We have CMU, we have Andrew, and there can be a relation saying that the CMU is founded by Andrew Carnegie. So that is the edge founded by for example, classic closed schema. And there are also many attributes that are associated with them. For example, the name of CMU, the alias of it, the type of it, and also the descriptions that are associated with them. So how to use this information actually is the key of making knowledge graph useful for information retrieval. So, and also to see that make a difference with what people usually use knowledge graph is that, for example, nowadays in Google, if you type in who founded CMU, you can actually find the answer from Google's knowledge graph. But the coverage of this question answering, maybe even for Google's knowledge graph and their traffic, maybe it's only 3 to 5%. And here, what differs from that is that instead of only trying to find information that can be directly answered by a knowledge graph, what we want is that to bring the information from an existing knowledge graph to an information system. And that instead of only influence part of the search traffic, we want to improve all of them. For example, not 5% of queries, but 100% of them. And also we want some general and robust solution that not only covers the semantic scholar, but maybe also the general domain, web search, and maybe also many different domains, and medical search and legal search. And we want the solutions to be robust. That is, it shouldn't be something that when there is information in the knowledge graph, then it works. We want it that whether it is write the correct information or noisier information, or maybe something at a lower recall, but we can always leverage some part of it and can overall provide some overall improvements. So it is the overall entity-oriented search framework starts very simple. So we have the query, we have the documents. The first step is to find entities that appears in them. So we can use a typical entity linker and to find the entities in that. For example, the query natural language user interface can be annotated to the entity NLUI in a knowledge graph. And also the document maybe have NLUI and also database in it. But one weakness of the previous entity linker is that they mostly focus on precision and maybe also only several categories of named entities. For example, even in last year's TAC KBB computation, I think there is only 3 to 5 categories of entities that are the candidates to be linked. But to be able to have a very high coverage to, as I say, influence the overall search traffic, we want something to have a much higher coverage and a recall. So we developed a very simple entity linker that tries to link almost everything, as many as possible. So first of all, we relax the precision constraint and we focus on recall, even maybe it's noisy. So here, introduction, is it an entity or not? It's not that clear, but as long as there is a such entry in the knowledge graph, we would like to link it first. And then we want to not only say the several categories, NLUI or database, but maybe everything, say query language or more general, some noun phrases or concepts. We want to annotate all of them. So this actually makes a very huge difference. If you restrict your linker to precision and several categories for a web page, I think even in Google's production entity linker, the one they have released, there is on average only 5 entities linked per document. So think about the whole document. If it's only 5 entities in it, then it's very hard to say those 5 entities can represent the general meaning of the document. But with this relaxation, we actually can have about 100 to even on average 300 entities linked per document. And all the web search queries and semantic scholar queries, those I have seen during my internship, I think more than 80% of them have been covered by some entities in Freebase. So this is actually a very dense annotation, and they can provide a very good representation of the text either in the query and document. So I call it a background entities, so that instead of representing text as the words appear in it, here we use entities to as a representation of them. So now the query and documents are represented in a background entity space. And very easily just do an exact match in the entity space can provide us some advantages already. For example, it gives us a much better chunking. We know that the whole query is actually one entity. You should match them as a whole because it is a minimal, meaningful concept. You shouldn't match something, say, natural language or user interface, but you should match the whole phrase together. And also, it automatically throws away the stop words and, of, in. They are all thrown away. And also, you have some automatic pseudonym resolution from your entity linker. You know that the NLUI and the natural language user interface, they are the same entity. So you don't have to do the pseudonym resolution or query expansion individually, but with that entity linking, you already can match them. But this is actually a very beginning step of it, right? We just move from words to entities. And if it is only entities and nothing else, then it's not a knowledge graph. It's more of, say, a better set of vocabulary that is cleaner and maybe more meaningful. What makes knowledge graph more interesting in the first place is all the relations and the structure semantics associated with them. For example, we know NLUI are published in all the venues, and database may be published in the other venues. So we can see that here we can bring in both the general domain semantics, say the Wikipedia page of them, but we can also add in the specific domain semantics, say all the venues that can associate with these entities. But this is still very sparse. So on most of the cases, if you pick an entity in the query and they pick the other entity in the document, on the majority of the cases, more than 90%, there is no edge between them. And furthermore, maybe all their neighbors are not the same at all. So this is very sparse and can make your system very fragile. So what it is actually much more useful and easy to use is to use knowledge graph embeddings. So instead of using the raw graph edges or the random walk in the original graph, it is much more beneficial to train a graph embedding, say line or trans-in embedding, or even escapegram using the edges to map all those surrounding neighborhoods of an entity as a continuous vector in entity embeddings of them. So then as a result, you can connect all the entities by their similarities in the embedding space. So now even if they have no shared neighbors, but if their neighbors are similar and maybe they have a similar structure, maybe a similar relation types, they will be mapped as a relatively similar space in the embedding space. So now everything is smooth and it's much easier to use. So then besides directly matching the background entities using exact match, the NLUI with NLUI, we actually are able to first mapping them to an embedding space. So we have the entity embeddings for all the query entities and the document entities. And now besides exactly matching them, we can have all the soft matches, say between NLUI and the database, and also NLUI and the query language. So now that we know, maybe for example, a document, if it contains a lot of similar entities in that knowledge graph structure, maybe you have a much better relevance signals of them. So this actually works very well on the Semantic Scholar dataset. So this is the result from my last internship, already 2 years ago. So we started with back then the word-based Semantic Scholar search engine. So I think at that time it is based on Elasticsearch. It's a combination of words and phrase matches. We're adding the entities and its own background entities and its own exact match, nothing else. So it gives you about 5% of improvements already. But if you're adding the raw edges and trying to use the cosine similarity thing of their shared neighbors or the graph random walk distance, it is very hard to use, and in general, it actually hurts the performance because it is very fragile and too sparse. It's only that if you're adding the embeddings and adding the soft match using their embedding similarities, you can actually make use of that structure semantics associated with these entities and actually improve the ranking performance. So you can see that the gains comes from two parts. The first part is the exact match gains from using entities. And the second part is using the embeddings to adding the structured semantic information as a distributed semantics into the system. And also, what makes it more useful, I think, yes?
I wanted to ask, the first column here, do you still use learning to rank, or
Yes.
is this the default?
I think it's a previous one that is some weakly trained one. It has some learned parameters. It was an online system when I just joined.
Yeah, I think that was before the current learned model that we use, but there was some training of a small number of parameters.
Yes, it was some training, but it's not a lot of features yet back then.
How do you add the entities? Like, are the first two columns using the same model family, or are they completely different?
It's a linear combination of them, so you have one weight to train it the same way.
I see. So the entities are added in the learning to rank framework and
Yes.
combined with the.
Yes, combined with the previous one. Yeah,
Okay.
a very typical setup. I think today, if you want to add it in, it will be the similar setup. Yeah. Yes.
Are you ignoring the relationship between concepts and the query, between entities and the query?
For back then, the queries I see in Semantic Scholar, most of them only have one entities. So there aren't many relations between them. Yeah. For the relations between entities, I think it's more influential for the QA task. I have some other papers working on that. For general, not only Semantic Scholar, for web search traffic, most of these keyword queries and usually it's average 1.3 entities. And most of them have no edges in any knowledge graph. But we have embeddings of them, so we can later can see that it can be used to model which one is more important in a query. Yeah. And the relations between query and document entities are mostly by modeling the embedding similarities, by mapping the relation space to the embeddings and then compare them. Yeah. And also we have done some very thorough analysis back then, so the improvement of those parts are mostly in the Semantic Scholar queries where the word-based system failed. So it is because that it failures to understand the concept, the chunking errors, or without the background knowledge. Within this part, it's not improving those that the Semantic Scholar already performing well, but it's the part those back then Semantic Scholar was struggling with. So I think it's a very nice complementary of the word-based model to me. So the lessons I learned, I think, from this part is that knowledge graphs can influence our search engines or maybe in general information systems in a very general and maybe much needed way. But it requires the right techniques to deal with it. So we have several customization thing to make sure the entity linking have a very high coverage. Also, we did not use a closed form schema, the exact structures, but use background entities and knowledge graph embeddings. And we also have many models after that, say, by joint learning the entity linking and entity-based ranking to combine all these parts together. I think those are the things that we need to. But with that techniques, I think knowledge graphs have the ability to influence your general applications. So, and later I think I make it more general, I think, to instead of only focus on search engines, but say whether we can use entities to improve the understanding of text at a large scale. So I call it large scale because it is very different from what we, I think, at sentence level or word level or phrase level. Because at those granularities, I think the current neural networks have done a reasonably good job. We have the sequence model, we have tensions, we have copy mechanism, we have all the different methods. I think at the sentence level, we have done a much better job than, say, 5 years ago. But for search engines, most times we are dealing with long documents. And at the document level, it's much harder. At least it's a different task. For example, for text classification, word removal distance just by combining words and doing a word level and combination of them, even in text classification, I think on documents it works much better than, say, LSTM. And in search engines, most of the times we found that even a simple, very simple background words works really great. And before you see that we have background entities, those are still background things, right? We break down the text into some individual items. So instead of saying it's a sequence of things or whatever, we treat it as a set of individual things. I think this is a very shallow understanding. I think we definitely should be able to do better than that. And the intuitions actually have been there for a very long time. So we have, for example, all the entities that appears in a news article about concussion and brain injury. So maybe that each individual concept only appear once or twice. But if that article is about brain injury or concussion, it's very reasonable to expect there have been many other related entities in that document. And if we are able to model their interactions or connections in a document, for example, the relations of them, the connections of them, how the different entities are centered around, around the different central entities, maybe we can do a much better job than, say, background entities. And for example, maybe we know that all the indicator, FDA, CT, and radiations are about concussion. Then we know that the concussion is the most important entity in the document. For example, they call it entity salient, or we know at least we should be able to do a much better job than counting frequency. So how should we do it? So we have the embeddings. It's very reasonable to say that we, again, mapping all the entities into that embedding space using any knowledge graph embedding models you want. Then we can connect them in the embedding space. So now we have an entity graph that connects all the entity pairs. Then how about we run PageRank or a graph convolutional neural networks or any graph-based ranking algorithm to model that graph based on embeddings and trying to pick which one is more important. But however, this one I have tried very hard, but it does not work at all. The reason is that the embedding similarity is actually does rather poor in modeling the connections or relevance between entities. One problem we found is a harmless problem, is that because it is a very high-dimensional embedding space, and it is very reasonable to say to assume any embedding models can do a reasonably good job in grouping things that are very similar to each other in a close neighborhood. For example, the brain injury and concussion, most times we can group them, say these two are very similar with each other. But anything that are further away, that might be partially related or not related, or even contradicted, maybe all have the same distance in a very high dimensional space. And so with that high dimensional space, we're actually only using a very tiny part of their similarities, but anything that is further away, maybe we do not have any modeling ability at all. So to address these problems, we have proposed a new kernel mechanism that instead of only using one similarity score to model the interactions between two entities, that maybe only make a good use of the cosine space from -1 to +1. If it's a raw embedded similarity score, maybe it only does a good job in the +1 part. But to make use of the whole range, the whole spectrum, we put the RBF kernel, the density estimation kernels, at each different range in that space. So instead of having one similarity score, now we have multiple kernel scores saying this one have a very high density in this kernel over there, and maybe a lower density of the other kernels that are further away to it. Then the interactions in that entity graph is no longer just by similarity. So it's no longer, say, more similar means better, but it's directly separating the similarity into several different ranges, each by one kernel. And then interactions are through the kernels, say, the similar kernels, all similar entities only interact with the entity in the most similar kernels, and the related ones interact with those in the middle, and maybe the background ones interact with those with the kernels near the cosine similarity of 0. And then you can combine all these kernel scores, for example, in a very simple linear models to have the entity scores modeling how it is connected to the other entities. And the whole things can be trained end-to-end by your task. So for example, let's assume that for each document, we have some labels saying one entity is more important than the other one. And so we can have the write down a learning trunk loss, say the positive entities should have a higher score than negative entities. Then if you take a gradient on that loss function to that Salience score, and it can backpropagate it to all the way to the kernel scores. So the kernels would transfer that gradients on the kernel scores to the expectation on that embedding space. So maybe these pairs of entities, their cosine similarity should be much lower than current one. And then this will be converted to that embedding space, and then to train all the embedding space and reallocate all your items in that high dimensional embedding space in a much better way. For example, not only those that are similar, but maybe also groups of entities that are related, unrelated, or conflicted at different ranges. Yes?
Sorry, where are the negative samples coming from? Are they
Yes.
important?
Yes, so we have actually two data sets to deal with it. The one you are most familiar with maybe the Semantics Scholar data set. So we have the paper abstract, we have the paper titles. So entities appearing in the paper title are considered as more important than the entities that do not appear in it. So we have some preference over there. And also here, there is another data set, the New York Times one. So it's 500,000 news articles, and all of them has expert written summaries. So the entities that appear in the expert written summary are considered as important, and those are not considered as not important. So you have some automatic kind of labels at entity level for the two data sets.
So all of the entities used in that loss function come from the same document?
Yes, so it is to compare which entity is more important for one document. So I consider it maybe as the next step after entity linking and entity co-reference to determine that not only which entity appear in the document, but which entity is more important in the document. I don't know, question. Yes.
So my interpretation is that you are learning more expressive similarity function.
Yes.
And so the question is that when you previously used cosine, did you also learn the cosine?
Yes, yes. You learn that embedding and you put it in cosine, yes. Yeah. So but with cosine, it's very hard to learn not only for this task, but later for many other tasks. Yeah. We have all the comparisons. Yeah. So it's actually here. So this is the New York Times data set, which entity appears in the summary or not. That is the Semantics Scholar data set, which entity appears in the title or not. So you start with frequency, which gives you something at 0.4 precision at 5, I think is good, but I think it's only halfway. And if you put in all the features, all the linguistic features, dependencies parsing, CCG parsing, also semantic row labeling features and entity co-reference features, and even just embedding votes, and you combine them all together in a feature-based method, you can do better than only frequency. And then if you only use the embeddings and learn that cosine similarity, it actually gives you nothing for this task. So only if you combine it with frequency, you can get the same level as frequency. If it is itself alone, almost the training loss never drops at all. It's only that if you use that kernels to trying to learn a different, more explicit conversion from a similarity to the interaction strength, and that gives you a much better improvement. Even compare with the state-of-the-art feature-based methods. So And we also have similar results in modeling events. So we have FrameNet events that we extracted from the news article, and to see which events appear in the summary or not. We have almost exactly the same observation, that something appears, something I learned with kernels between entities and events are much more useful than the row cosine embedding similarity. So a quick recap here is that I think, yes?
Do you have intuitions why precision is very low? Like the absolute precision, not relative.
I think it's actually pretty high. I think 0.4. 0.4 is pretty high. 25, I think, is because for semantic scholar, there's only very few entities appear in the title, 2 or 3. So your positive examples are very small. So if you pick some, it's also, I think it's not an easy task, right? It's if you only, at least I don't think frequency is able to predict which entity appear in the title, I would say. But I think at least over here, 0.4 precision and 5 is you're picking the top 5 and 2 of them are correct. I think it's okay. Yeah, but it is a much harder task than, say, sentiment analysis. But I would say it's easier task than overall web search. In web search, if you get 0.4 precision and 5, I think it is pretty good. Yeah. So I would say the large-scale text understanding is a very different task than understanding things, say, at a sentence level or phrase level. And there are many previous attempts to it, for example, topic models and document-to-vector. I would say entities and kernels provide a new path to it. And later we will see how this can lead to search engines, whether it can be really useful for some real online system. But before that, let me answer some of you maybe already concerned, say, why do we need entities? Why not we just do deep learning and use neural networks to learn everything together? So say, let's forget the entity part for a while. Let's see, we go back to the word space. We have the query, we have the document, we have all their words. Why do we do entity linking? We just do word embedding, and we use deep learnings to map them in the embedding space. Right, we use deep learnings to map everything in the embedding space. So maybe all the semantics can come from the neural networks that we do not need an explicit structure. Well, we still have the harmless problem, right? Even in the word space. We maybe have Tokyo and London be grouped together, for example, in the skipgram or word-to-vector or globe space. But maybe everything else are at a similar distance in that word space. But also, the things that search wants maybe is very different from what many NLP tasks wants. For example, London and Tokyo, they might be very similar in a text classification task. But when you are searching for something in Tokyo, you might not want something in London. Well, we have the kernels, so we can use the kernels to learn everything, right? We can organize all the words by their similarities, relatedness, maybe also background or conflict. So if following this idea, what are the models we come up with? So we have the query, we have the document, we have all the word embeddings. So we can use kernels to directly model their interactions in the word space. Say how the query words similar with that document words and pull that back to the kernels. And you have the kernel scores, you can, for example, using a log sum to combine all the kernel scores into some ranking features. And then you pull that ranking features into a learning trunk system. And you combine them to a ranking score. And because now everything is smooth, if you have enough training data, you can learn the whole thing end to end. You learn the learning trunk part, you can also learn the word embeddings. So everything is actually customized for your final ranking loss. And furthermore, you can also add in more complex neural network structures into the system. Instead of only have word embeddings, you can put a CNNs upon the word embeddings to compose that word embeddings into n-grams. So now you can not only matching the words in the kernel and the embedding space, but you can also match n-grams. Furthermore, it's not only, say, matching bigrams to bigrams or trigrams to trigrams, because everything now is in the embedding space. You actually can matching a word to a trigram or a trigram to a bigram. So you can have both the same length matches, but also cross matches. But furthermore, you can just combine them all together using a mean pooling or whatever as ranking features and has a learning trunk layer to combine them. So again, if you have enough data, you can train the whole things end to end all together. Not only the ranking part, but also the convolutional neural networks and also the word embeddings, all by your relevance labels. So let's see how it performs. So again, here are the results. We use a lot of training data. So we have access to the search logs from a Chinese search engine company, Sogou. It's maybe now the second biggest one. So here we have 500,000 of user clicks. So we use that clicks to train the whole model, the word embedding, the ranking layers, and n-gram CNNs all together, and using the user clicks to also do the evaluation. We also have the similar results from the Bing search log. By there we have somehow also 500,000 of search logs, user clicks, so we can train everything end to end. So we start with a BM25 or word-based match, the one you get from Elasticsearch. We have all the features, all the retrieval model scores, all the document quality scores. We combine them together in a learning trunk system. Yes, we can do much better than the unsupervised Elasticsearch model. And if you're adding the raw word2vec, maybe also use the same kernels, but fix the word embedding part and do not train it at all. You can do a little bit better, but only 3% better. But you have a lot of those information, but it's only 3% better. And if you do not use the kernels, only use that raw cosine similarity, and you learn all the embeddings end-to-end using your relevance labels. So it's all customized, fine-tuned for your final task. And it can be trained to be something very different with word2vec. You can get 10% improvements. But adding the kernels, things are much different, and you have a huge jump from the either pre-trained word2vec or the one you train end-to-end but without using kernels. And furthermore, you're adding the n-grams within everything kept the same, but you're adding CNN layers upon word embeddings to n-gram matches, and you can do even better. So you can see, compare over there the Convolutional K-NRM to what we have learning trunk. I think learning trunk was a state of the art, say, 3 years ago, and now we almost have doubled or 50% better at least than the state of the art 3 years ago. And this performance is actually even better on the Bing search log, especially the n-gram part. The reason is that this search log is in Chinese, and in Chinese, we have the word segmentation. So many phrases in English is actually one word in Chinese. Say the Carnegie Mellon is one word in Chinese, and ear ring is also one word in Chinese. But in English, we need a phrase, we need n-grams much more. And there, we can have even higher gains at the n-gram part. And also, we can see that with the kernels, it does show that more similar does not mean that it's more relevant. So here are the performance with each individual kernels. The blue line is all of them combined together. The orange line is the learning trunk feature-based baseline. So you can see that with the similar kernels, that with the cosine similarity of 1 or 0.9, it actually contributes very little. It's almost performs the worst. It's even worse than those in the background part. What makes a huge difference is those that are partially related. Those in the 0.5 range and those in the negative range. So this one and this one are the ones that contribute the most. And we can see we do have found very interesting matching patterns from the search log. So here are the query term, the document term, and those are those that contribute the most to the relevant score. So mostly see from the partially related kernels. And the red ones are those not contributing at all. For example, for the query that contains the word Maserati, the document that contains Ghibli, a car type of it, actually provide a more detailed explanation of the search intent, so it is more useful. But the car is that everybody that is searching for Maserati already know that it's a car, and having that word in your document is not contributing at all. And also we can see many very typical similar pairs in the typical word embedding space. When you are searching for son, maybe you are not searching for something about a daughter. And website and homepage, AT&T and Verizon, those are not very useful relevance pairs. But what is more useful is those that are more related to search intents or search tasks. You want to find a reader for your PDF, we want to find the customer service for BMW, or you want to find a search for the missing airplane MH370. So all those things are that are being learned from user click patterns, and those are the word embedding similarity interactions that search engines actually want. That maybe with a word in word to vector or glove similarities that will not give you. Then do we still need structures or knowledge? Right? We have everything learned end to end. We also have n-grams to have phrases. We also have Salience to learn the phrase level match. So what is the role of entities when you have a very large amount of training data and have your neural networks? Well, we can still put entities in it and see how it performs. So we have the query, have the document, we have their n-gram embeddings. Then we can do entity linkings, have all the entities in the document, entities in the query. We can also embed them. So we can put the kernels between all pairs of them. So we can have word kernels, n-gram kernels, entity kernels, but also because now again everything is an embedding space, we can also compare entities with words and phrases. So we also have the cross-match kernels. We combine them all together as ranking features and then as a learning trunk layer. And furthermore, we have all the background information from the knowledge graph. We have their relations, we have their descriptions, we have their types. So how about we also put them, for example, as external memories upon those entities. So we can have the description embedding using CNNs or sequence to sequence. We also have the relation embeddings or type embeddings. So you can use the attention mechanism to combine them together to the entity embedding, just concatenate them or put a layer upon them to compose them. And then to use that information also in that search process. And if we have enough data, again, we can still train everything end to end. From the ranking score, we have the gradients. We learn not only the word n-gram embeddings, but also the entity embeddings, but also all the way to that attentions and to learn the description embeddings and also the type embeddings. So the whole model can be trained all together directly using your relevance labels. And see how it performs. So we start with that n-gram matches. Then if we only add in the entities without any background information, so it's only the entities, maybe it's only entity annotation, the entity embedding learned from your data. It works better, but it's only a little bit better than those you already have from n-grams. So we found a huge difference with that neural space compared to the previous feature-based methods. Because if you are matching n-grams without the neural networks, you can only do exact match. And you have to, for example, enumerate all the possible n-grams and compare all of them. So you have the chunking noises and maybe not, maybe introduce a lot of noises that maybe it's very hard to deal with. But with neural networks and CNNs, you can learn somehow to some extent which n-gram is more meaningful and how to compare n-grams both exactly and softly. Then within that setup, if you're only adding the entity annotations, it does not give you as much as you can have from the previous with feature-based methods. What makes a difference is the background knowledge from the knowledge graph. If you add in the descriptions, the types, and also all the relation embeddings into that mix, and that's where you can get the huge gains upon what you already have from the neural network model. Then another question is that all these things are using search logs. So in Semantic Scholar, we do not have, say, 500,000 clicks that associated with 1,000 query or whatever. And in many public domains, maybe there is only 100 training queries. So in this case, how can we use all these models? So say we have that Convolutional K-NRM model, we have word embeddings, n-gram embeddings, and learning trunk layer. How about, let's say, we first pre-train something from the search log. So we train everything here using the bin search log, for example. And then we can only use that train that learning trunk part on your public benchmarks, for example, on track where it's only 100 or 200 queries and maybe 10,000 labels. So you can pre-train all the embeddings and use that pre-training embedding, which is very different from word to vec and other pre-trained word embeddings. And then use that embeddings just as a feature extractor to extract the features for your other search tasks. And with entities, we have the New York Times corpus. So we can train all those apart using the entity Salience task. So we don't have the query anymore, but we can use the documents and to know which entities are important in the document. So we can learn the entity embeddings and maybe also use that to learn the n-gram and word embeddings. And then we can all pre-train this part And then for your task, we're only using the last layer to be trained, so it's only 10 or 20 features. So here it's trained on a news corpus and on entity Salience task. Then all these embeddings or the knowledges we have learned from that task. And then we use it for a search engines with limited training data. So this is where entity actually makes a much larger difference. So here we have, it's on the web search dataset. So these are the feature-based learning trunk. Those are with knowledge graph embeddings with relations in freebase and trained entity embeddings using knowledge graph inference models. We have 6% improvement. Then if you train all the word and phrase embeddings using Bing search log, you can do better than learning trunk features, maybe 9%. If you use entities, I think it performs a much better job in transfer your knowledge. It's much cleaner, it's a more meaningful concepts. So the things we brought in from the entity Salience task actually can perform much better than what we have learned from the Bing phrase. So here we can see that for information retrieval, deep learning has now taken off, I would say. But we need very different tasks than very different models and different ways to train it. And here what we found is kernels are much more useful than cosine similarities or even LSTM we have tried. And entities here performs a very unique role even in the neural network space. It can help improve the generalization ability of neural networks. When you do not have enough data with entities as a pre-training part, it performs much better than words. And also, even with the large-scale training data, with entities, it serves as a role that you can bring in additional signals from your knowledge graph to your system. For example, maybe with neural networks, we are now able to learn which one is a phrase and how phrase should match with each other based on user clicks. But I don't think now we are able to learn the whole Wikipedia. We can learn all the background knowledge from the Wikipedia directly from our search log. I think that's a part we found now entities are also very useful even within an end-to-end learn neural model. So to have a recap of this talk, we start with the full-text search engines. We add in the knowledge, we have entity-oriented search, we have background entities, we have knowledge graph embeddings, so we have a better chunking, we have pseudonym resolution, we bring in the relation information to the mix. So we can do much better than feature-based learning trunk. So if we add in the neural part to it and we can have a better large-scale text understanding, we can do a better job in predicting which entities are more important for a news article or for a semantic scholar paper than just counting frequency or using features. And along the deep learning part, by adding the neural models, we can learn a kernel-based soft match between the query and the documents, and not only works for one data set, it works for a Chinese search log, for English search log, and also we can pre-train things with the search log and bring it to the public domain. And these two parts actually can work together. So if you have enough training data, you still can add in the entities and bring in the background information, and still can improve your overall ranking accuracy. But furthermore, if you do not have enough data, entity provides you a much easier way to transfer your knowledge, maybe you learn from other tasks, and to improve the scenario when you do not have enough data, but you still can use embeddings and with a much better performance. So overall, I think this all combined together can provide us a much better overall ranking accuracy on the search log scenario. The most again we can find is almost doubling the feature-based ranking model. I think it's only the progress our community has made in 3 years. I think it's a very huge step forward. And also, when you do not have enough data, the relevance labels are much harder to label than many other tasks. But we still can do maybe 30% better on many of these scenarios. And all the things I have discussed can work well not only for, say, one data set. It's for multiple different data sets on different domains. We have web search, we have academic search, we also have medical search, although it's not in this talk. And it can work well for multiple different knowledge graphs. I have tried free-based Wikipedia, also control vocabulary. And furthermore, we also have the semantic scholar simple knowledge graph where we use Wikipedia entities by adding the author and value information to it. It still can be useful for academic search. And it also not only works well for English, but also works for Chinese, so it's multiple languages already. So in the future, I think, again, back to our motivation, we want to build a more intelligent system and it's not only a retrieval tool. And I think the path I wish to do here in AI2 in the near future will be twofold. One is through a better understanding of our language, and the other is to better model knowledge. So for the language understanding part, we have our human language. It can be in other different formats, right? It can be in query documents, can be dialogue response, and can be question and answers. And I have shown some ways to bring in some structured semantics to it. I think in the future, we can think about what are the better structures, what are the better nodes, what are the relations we want. And we can see we have used distributed semantics with deep learnings to improve representation of them. We also have seen that how they can interact with each other in the first step, right? So in the first part, we can say we use the embeddings. It does a better job in modeling the relations and structuring information in a knowledge graph. And in the later part, we can see even with distributed semantics, bringing knowledge can still be helpful. I think in the future, there are many opportunities over these areas that we can explore. In the human knowledge modeling part, we have shown that how we can utilize that knowledge into our real information systems. We have also shown how we can better represent them. We have background entities, we have the knowledge graph embeddings. We also have the end-to-end learn way to bring the descriptions and types and relations from a knowledge graph to a neural network system. I think it's also interesting to see how we can better acquire knowledge for our current task and how these three parts works all together. For example, given a task, as we think about, for example, given the current task and the current solution, maybe we should think in the beginning, what are the knowledge the current model do not give us? Say what a neural network system cannot bring in, cannot learn, and then what are the knowledge and where are they, and how can we acquire them? And then how can we represent them, and how can we bring them to the current system? Maybe in the future, this whole part should be learned all together, end-to-end, or using reinforcement learning. And I think this part is very premature, and there are many things to work on. I think at the end, I wish to thank all my co-authors and mentors, and both, I think, previously here in AI2 and also in Samuel and Microsoft, maybe also in Tsinghua, I guess. Yeah, that will be it.